So I'd say I'm a normal guy, but I've always liked stupid projects. The CPU is quote-unquote alive. Problem is, it is not that simple indeed. This is up. Nothing except grass to touch. It really works based off luck. 1,129 warnings. Oh my god, it's working. No way. It is working, dude. And you see, I've always been into computer science, that's the term. Kind of a nerd, so to speak. But I never went into actual computer science for college because the tech market was looking pretty damn bad. But one day, I had this truly brilliant idea. What if I made my own computer? Like, not take a motherboard and throw in a GPU, CPU and whatever and call it a computer and call it a day. No, I mean make my own computer, my own computing chip, my own machine to compute instructions that I do, my own silicon stuff, you know. And yeah, to do such a project there is a little bit of work to do, and at the end of this video I will give you all the resources you need so you can do it too, like you can do your own CPU. Before starting anything, you have to see your CPU as a machine, kind of like your car. But you know, it's a CPU, it doesn't have wheels or an engine or whatever, it just does math. Boolean math to be exact. And Boolean means that we represent the data using zeros and ones. And you can tell this machine what to do using instructions that you format in a binary language with, like, the code names for add will be 00110 and whatever. It's like code names in binary. But here we focus on switches called transistors that are either on or off. And you can organize these switches into logic gates, and you can organize these logic gates into logic that you can manipulate to create a machine that do math. What the CPU does is actually very simple. You just give your CPU a program, the CPU will fetch the instructions, then the CPU will decode the instructions, like what is this asking me to do, then it will execute the instruction. I don't know, add or subtract, and once the CPU has a result, it can use it to operate on system memory, or it can simply store it in registers, which is a very small piece of memory, to use it later. So we just listed 5 steps for the CPU to execute an instruction, and let's review how each of these steps are ensured. First, the fetching process. The CPU has a piece of memory that we'll call instruction memory that stores our RISC-V assembly program that we converted to binary, aka machine code. To know what instruction to fetch, we use a program counter that increments on each clock cycle to fetch the very next instruction, and so on. Then the instruction is read by the control unit, which decodes the instruction to generate control signals sent to the other units in the CPU. This step is also the moment where we can retrieve data from the CPU's registers. In the add example we saw earlier, we can see that in the instruction we specify both source registers and the destination register. We can also use hard-coded data from the instruction itself, depending on the instruction type, and this data is called immediate and has to be processed by the little unit at the bottom called the sign extender before use. Then, the execute stage is mostly a matter of getting the math going. This is all abstracted into the ALU, which is essentially a 2-input multipurpose calculator. The ALU can take 2 inputs, and the control unit will decide whether the second one is from the registers or the immediate. After that, as stated before, we can use the result as an address to operate on memory by performing a store using data incoming from the registers or a simple read, and we can also bypass this memory stage altogether to directly write back this whole new piece of data back to the register for later usage. This is called the write back stage. And there you go, that's really all there is to it. But how do we go from this idea of a CPU to an actual working CPU? Like, what do we do? So to make this project a reality, we'll have to make a few choices on the design. First, we have to choose an instruction set architecture. Long story short, an instruction set architecture, or ISA, is just a way to describe what binary language you use, and so what binary language the CPU will understand. I chose to go for RISC-V because it's free, you know. Don't pay for a instruction set architecture. And then to make the actual design, I will use System Verilog, which is an hardware description language, or HDL. This allows me to create digital circuits using code, which is extremely nerdy. Like now that I say it out loud, and to make sure the HDL I'm writing does not make anything stupid, which, you know, it always does, we are going to use a simulator. So we can run test benches on it and check whether the code is doing anything stupid, if there is any bug or whatever. For this part, there are many tools to choose from, and I chose to go for CocoaTB and Verilator because most of the other tools are proprietary. I don't want to pay for this, so I chose CocoaTB, which is a Python way of writing test benches, and after everything is installed on my personal computer, I can start running the project. And then starts the painfully long list of instructions. I have to implement instructions one by one, starting with load word. The first ones are the hardest, because basically I start from nothing and I have to build the first logic blocks, like the arithmetic unit, the registers, the memory, the sign extender, whatever, you know. I have to build all of this from scratch. And I also have to simulate each and every new block that I add, so really the first ones are the most painful to implement. If you really take your time and follow along, it's really doable. In starting off with only one instruction and really take your time to add them one by one is a great way to avoid any undebuggable problem. I don't get it. It's like, do I really have to do it twice for this to work? And after a very long and very painful list of instructions to implement, I've finally done it. I finished. Like all tests are passing, my CPU runs the entire program on simulation. Oh god. And you know it's only the start of the problems. I actually wanted to use the CPU in the real world. To do this, we'll use an FPGA. An FPGA is a chip that has reconfigurable logic block, which allows us to pretty much configure it into any logic we want. And in our case, we'll use, well, the CPU logic, you know, like we want to run the CPU on an actual chip. This FPGA board is not even mine. It's from my school. And the problem is that it's not as simple as just throwing the HDL code into a translator called Vivator, which will translate the HDL into actual FPGA fabric. You see, the core needs to communicate with the outside world, because, you know, if it doesn't communicate with anything, you can't give him a program, you can't drive anything like motors, LEDs, or whatever you want to plug to it. So it's like having a computer, you can't plug any keyboard, mouse, screen, or whatever in. Like, it's just a space heater, basically, you know, it's just useless. So it's just convenient and mandatory to have an external interface to communicate with the outside world using XI, which is a nerdy protocol I won't get into. So the plan sounds simple enough, just add an external interface to add some memory and stuff, but it was not that simple. When I was doing some work on simulation, I took a lot of shortcuts in the design that started to be a little too obvious. It was not working at all, man. It was just not. And so, yeah, turns out having a working simulation does not mean having a working FPGA implementation at all. Like, at all, man. It's not working. It was just not working. But after a lot of reflection, I finally got some signs of life on the board, on the LEDs, you know, like the CPU was doing something. It was tinkering around. But immediately after, I realized something was infinitely wrong, like very wrong. Got some signs of life from the CPU, and the problem is, it is so unreliable. This thing literally works based off luck. You see, I realized there is something called clock domain crossing. Long story short, my XI interface and my CPU were running on two different clock frequencies. Depending on the two clock frequencies, two clocks rising edge can happen in a very narrow timestamp, which makes the design not close on timing. And this is very bad. Like, my actual CPU was non-deterministic. It was working randomly. Absolutely not what you would expect of a CPU, you know? Like it was working based on luck. There are solutions to deal with clock domain crossing, but I thought to myself, what if I just yeeted the other clock and used only one? And so this was my big brain moment, big brain move that allowed me to go around a problem, and the core still did not work. So only turn this LED on, and not all four of them. I'm saying this because it turns all four of them on. My logic was so wrong. I even wonder how it passed simulation. On the spot it made sense to me, because it was my first time. I was like, oh yeah, it should just work, but I relied on very sketchy stuff. I wrote some piece of logic. It was full of bugs, alright? I wrote a whole block of stuff. It took me an hour to just, you know, find all of the little bugs and syntax errors. After a lot of very happy tinkering, I think I finally got it to somewhat work and get it stuck on an infinite loop, effectively doing absolutely nothing, which was a big achievement. So now the CPU can do reliably nothing. Now, I know that's very exciting, but we have to move on to an actual program. And what better program to do than to blink LEDs? This is just so exciting. To do so, I'll use the XI interface from before to hook up my CPU to different devices, given the fact that my XI logic is not flexible at all. Like, it is just so bad. So I really had to do some very deep software witchcraft to manipulate my cache into making it writing the right data. Like, that was just so bad. Back my cache was running 048C10 and it was writing back a 0 back to this. At the end of the day, I succeeded in manipulating my cache to write the actual LEDs. Reliably, it works. Like, it actually, it's this one. Okay, and now the moment of truth. Oh my god, it's working. No way. It is working, dude, look at that. And ladies and gentlemen, after a long struggle, I present to you the Holy Core project.